Okay, so we're now ready to get into the nitty-gritty details of a first-order integrated rate law. As I set this up, I'm going to talk to you a little bit about some of the limitations that we're going to analyze first, and then later on in a video down the line, we're going to talk about how we're going to get around those limitations. But first, the limitations. Whenever we talk about the integrated rate laws, we're going to be looking at simplified reactions, namely that they only have one reactant, in this case reactant A, going to form products. We're not yet going to analyze kinetically systems that have multiple reactants. So we're not going to look at A plus B going to form products. The reason being is right now, if we had A and B reacting, that would be two variables that change in time, and that would require us to do multivariable calculus. Now, I know some of you would love to be able to do that, but that's not the analysis we're going to take a look at. Later on, I'm going to show you a way to take what looks like a multivariable problem, and with a little bit of chemical trickery, a little clever experimental setup, we're going to get multivariable problems to turn into monovariable problems. So here in the big gray box, you see the calculus behind a first-order reaction. I'm not going to spend a lot of time walking through the calculus. If you want to write down all the calculus, you probably want to pause the video and write it all down. Ultimately, what we're going to care about is the stuff down here in the box. But essentially, here's the setup. So I have one reactant A going to form products. So the rate of this reaction is going to be equal to the loss of A over time. And you know it's the loss of A because A is a reactant, and so we have this minus sign in front of it. And it's going to be equal to K times A to the first power. So I know already going in that this is a first-order reaction. Okay, I'm right now limiting myself to first-order systems. And so from here on out, the rest of it is going to be a calculus analysis where I have to move like terms to the same side of the equality and then do some integration. So all of that is shown throughout this analysis. If you want to take a closer look at it, go right ahead. But the end result is this. Remember, A here is going to be concentration of A. So at some point, as you can see here, I dropped the brackets, but we're still talking about the concentration of A. So eventually we get down to a result that looks like this guy here. That is the natural log of the concentration at some time later on minus the natural log of the initial concentration, that's what the little superscript 0 means, is equal to negative kT, where K, of course, is the rate constant of the reaction. I can take advantage of a property of natural logs. If you take the difference of two log statements, it's equal to the ratio of one log statement. That's what I've done here. And then to go from here to there, I've just taken advantage of another property of logs, namely, I've taken the exponential of both sides of the equality. And so really what you need to pay attention to is here in the box. The concentration of our reactant at some time, A, is going to be equal to the concentration of our reactant at the initial time, A0, and that's equal multiplied by the exponential negative kT. So I need to harp on this one more time. This only applies to first-order systems. The equation in the box can only tell me how much A I have at any time t later on, assuming that A reacts with first-order kinetics. This only applies to first order. All right, so let's take a look at some of the practical implications of first-order integrated rate laws. This next slide here, I'm showing you the decomposition of dinitrogen pentoxide. Now, I'll tell you in advance that this is a first-order reaction. We haven't necessarily done the analysis to prove that it's first order, but I'll tell you that it's first order. And so I have here on this table, I have a whole bunch of different concentrations of N2O5 at a whole bunch of different times. Now, one thing I can do with this data to begin to analyze it is I can go ahead and graph it. I could, as I would do on this next slide, so you might want to pause this for a second to write down the concentration and time data here, because on the next slide I'm going to do a quick graph of it. So if I take this concentration versus time data, I go ahead and graph it. So I'm going to have the concentration, whoops, change that to the pen, I'm going to have the concentration of N2 0.05 over here versus the time. Now this is a first order reaction, so N2O5, as we now know, goes away like an exponential decay. So the concentration versus time graph is going to look something like that. If you want to put in specific concentrations and mark them off over here and put in specific times down there, you can certainly set up a nice quality graph. But we know that exponential decay has this sort of curved shape. And that's great. The data looks beautiful. But curved lines tend not to be very helpful in science. Curved lines aren't helpful for prediction. So I'm going to take this curved first-order graph, and I'm going to show you how to turn it into a linear first-order graph. So remember, we're still sticking to first-order kinetics. Everything I'm doing here applies to the expression that rate equals k times a to the first. This is all first-order reactions. Now you remember from 2 slides ago, we eventually sort of derived using calculus this equation here, that the natural log of a minus the natural log of a0 equals negative kt. With a little bit of rearranging, I can get this equation here, simply by moving ln a0 over to the right-hand side of the equality. And then if you squint at this guy, you can see that this middle equation is actually a y equals mx plus b. So in other words, if I were to graph the natural log of the concentration of A versus time, I'm going to get a straight line because my natural log of A is my y value, my time is my x value, and then the slope is going to be k, and the y-intercept is going to be the natural log of A0. So that's what you see me writing down in this table over here. I've taken the raw data from my experiment and I've converted all the concentrations of N2O5 into the natural logs of concentrations versus their corresponding time. So on the next slide, I'm going to show you the graph of this particular table here. And that's going to look like this. I now have a first-order straight line relationship. So this first-order relationship, again, everything I'm talking about only applies to first order, gets me this nice, quick, straight line, the slope of which is going to be equal to negative k. So this is how real chemists will collect data. They'll go ahead and collect concentrations over a whole bunch of times. And if they were to graph the natural logs of those concentrations versus time, and it comes out to be straight, that's another way for them to determine that it's a first-order reaction. Now, earlier in the previous video, I told you that we're going to look at second-order reactions and zeroth-order reactions. Those different reaction orders will have their own straight-line relationships. We'll see those in the next video. But for now, if we graph the natural log of our reagent concentration versus time, and it comes out to be straight, that tells us that the reaction's first order, the slope of which would give us the rate constant. This is actually how real chemists might start to collect this data. One more issue associated with first-order chemistry that I want to talk about, the issue of half-life. You've surely heard this term before, but half-life is quite simply the time it takes for half of the reagent concentration to be depleted. So you go from 1 molar of stuff down to a half a molar of stuff. So it's the half-life. You often see half-life in the context, of course, of radioactive decay. We're concerned about, if we run a nuclear power plant or we're trying to dispose of nuclear waste, how long do we have to store this stuff safely before it drops below some threshold level that could cause us health concerns. So here's how we derive half-life for a first-order reaction. Again, first order and only first order. Half-life is abbreviated T sub 1/2, as you see there. So one of the results of the calculus can look like this. In the previous slide, I actually had written that it was the natural log of A over A0 equals negative KT. Here, what I'm doing is I'm flipping A and A0 so I get to lose the minus sign here on the right-hand side of the equality. At the half-life, once I get to the half-life, my concentration of A is going to be 1/2 the concentration of A0. So now if I plug in A0 over 2 in for A right there, I get this relationship here. Natural log of A0 over 2 is equal to KT1/2. As you can see, the A0s are going to factor out, and I have the natural log of 1 over 1/2, which is just the natural log of 2, and that's equal to KT1/2. Then I could solve this overtly for the half-life. T1/2 is equal to the natural log of 2 over K. And all chemists know the natural log of 2 because we know the half-life equation for first order is equal to 0.693. So, if your reaction is first order, you can quickly find out how long it will take for half of the reagent to go away by simply applying the half-life equation. You'll notice that the half-life value is equal to a number, namely 0.693, divided by the rate constant. Notice the emphasis on constant. So half-life is a constant value. So to go from 100% of reagent to 50% of reagent is a half-life. To go from 50% of reagent to 25% of reagent is another identical half-life, so on and so forth. So each halving of the reaction takes the same amount of time. But that, again, only applies to what kind of reaction, everybody? First-order reactions. All right, so that's enough detail for first-order reactions. We'll start to practice this stuff in class. Next up in our future videos, we're going to give you the same amount of detail. We'll talk about the calculus, we'll talk about the graphs, we'll talk about half-life for second-order and zeroth-order reactions later on.